Welcome to a brief introduction to openvz, a screencast by Scott Dowdle. What is OS virtualization? It's where a single kernel allows for multiple isolated user space instances. Such instances, called containers, VEs, or VPSs, look and feel like a real server from the point of view of its owner. Containers can be thought of as a chroot environment with advanced extensions including multiple network stacks, dynamic resource management, group scheduling, and PID virtualization. Examples of OS virtualization products include Parallels Virtuoso containers, openvz, and the Linux vServer project. Also, container features are starting to appear in the mainline Linux kernel, and they've been adding them since 2.6.2.4. Now, most people are familiar with hardware-based virtualization products like VMware, Parallels Desktop, VirtualBox, those and others. And when would you want to use those over OS virtualization? Well, OS virtualization is only for Linux on Linux virtualization. And so if you want to run other operating systems besides Linux, then you have to use the hardware virtualization products. If you have special kernel needs, like if you need to run multiple kernels for development or testing or legacy systems, then hardware virtualization would be right. Or if you have where you need to run custom kernels with special modules or proprietary drivers that you have to compile yourself, then you'd want to use hardware virtualization. And another use is for people who like to check out the latest distribution releases, and they just want to download an ISO image and boot that up to check out the latest desktop distribution. That you'd want to use hardware virtualization for. Okay, so when would you want to use OS virtualization? When would you want to use openvz? Well, when you're virtualizing servers for the most part, although you can do desktop stuff in there if you really want to. But because OS virtualization is not a full emulation of hardware, it's a lot lighter weight. And I'll show you a demo where you can see what it looks like from the host node context and what it looks like inside of a container, and how it is indeed a whole lot lighter weight. As a result of that being lighter weight, you can fit 2 to 10 times more machines per physical host than you can with the machine or the hardware virtualization products. Also, there's not this hypervisor or this need to translate instructions from a fully virtualized machine to the host node when processes in a container need to access the hardware right to the disk or access memory. They can have access to native I/O subsystems. They talk directly to the single kernel. Another great use, which I use it for, is in educational environments. For system admin classes, I can take one physical machine, chop it up into 50 containers, and give each student their own root access to their own virtual machine, their own container, and they can install software, create accounts, and do whatever they need to do without hurting the physical machine. And if they mess up their container, I can easily regenerate it. And it's also good for service isolation. A lot of people use chroot configured server applications, like putting bind in a chroot environment or FTP server or what have you. Well, using containers and openvz allows a much greater isolation. Also resource management, so it's a lot better for service isolation than a chroot environment. Okay, and how do you install openvz? It's a fairly easy process. The openvz project provides package repositories for RPM and deb-based distributions, which covers a lot of Linux distributions. So you just configure your package manager to point towards openvz repository. Then you install the openvz kernel, yum install ovz kernel, or apt-get install the kernel. And once you have the kernel package installed, then you want to modify the /etc sysctl.conf file to change a few parameters. And then you want to modify your bootloader so that it'll boot your new kernel by default. Reboot the system into your kernel that now has openvz support. And then once you're running the new kernel, you need to install 2 additional packages: the vzctl program, which is the main control program for containers, and the vzquota program, which allows you to have quotas inside your containers. And when I say quotas, I mean disk quotas. And then you start the VZ service, and then you can start creating all the containers that you want. This is not, this is a real brief overview. I recommend you check out the OpenVZ User's Guide, which is a PDF on the OpenVZ website, or the Quick Installation Guide, which is a series of web pages on the wiki. And both of those are linked to on the very front page of www.openvz.org. Okay, so now you've got OpenVZ running. How do you create a container? Well, before you can create a container, you need an OS template. And that's kind of a fancy term that means installation media for a container. Now, with the machine or hardware virtualization products, you can just use the normal CDs or DVDs that you would boot to install a physical machine with. But since OpenVZ is OS virtualization and it doesn't emulate a whole machine, you can't use an ISO image or a CD to install a Linux distribution into a container. You need an OS template, and an OS template is a tar-g zip file that acts as installation media for a Linux distribution. Now, where do you get them? Well, you can create your own from metadata packages and some software that's provided with OpenVZ, or you can create them from recipes that you can find on the wiki for those that we don't have metadata packages for. We also offer a variety of pre-created OS templates that you can download from the OpenVZ website, and those are in two categories: official ones made from the OpenVZ project, and then a lot contributed by OpenVZ community members. And I myself happen to upload quite a few contributed OS templates for the distributions that I like. Also on the wiki we have a script that explains how to do physical to virtual migration, so you can take a physical machine and migrate it into a container. Okay, now I want to discuss how OpenVZ stores things on the file system of the host node, and the host node is the physical machine and the host Linux distribution that you installed OpenVZ on. All the configuration items are in the /etc/vz directory. There you'll find a top level configuration file called vz.conf, and that's the global configuration file. And then there's a conf directory inside etc/vz that has all the configurations for all the containers that you make. Each container has its own configuration file inside that directory. And then there's a directory called dists that has a few scripts in it that are needed. These scripts tell the main control program how to configure a network interface in the various distributions that we have OS templates for, how to set the host name and that sort of thing. Those aren't things you normally mess with, they just work, but I wanted to let you know that they were there. Okay, now where do the containers have their file system? Well, it's just a normal directory structure under /vz. Now in some Debian-based distributions, they like to put this under /var/lib/vz. So if you don't see /vz, look under /var/lib/vz. Anyway, there's a directory there called private, and inside of that you'll find a directory for each container. When you create a container, you give it a unique container ID number, and under the private directory you'll see a directory for each container that has the container's name. And inside of the containers directory you'll find the normal file system that you'd see in a Linux distribution. There's also a directory called vzroot. Inside of that you'll also see a directory for each container, and those directories are empty when the container isn't running, because the vzroot container ID directories are really the private directories bind mounted for when they're running. Okay, and then there's a VZ template directory, and that's where all of the template data is stored. So when you build a template using the metadata packages, or when you download an OS template from the OpenVZ website, you want to put that tar-g zip file that you downloaded into the VZ template cache directory, because that's where the system looks for OS templates when you're creating a container. And containers can have disk quotas, and the data for the disk quota information is stored under var vz quota. You usually don't have to look in there. Those are binary files. You don't edit them or anything, but that's where they're stored. Alright, so here's the basics of creating a container. OpenVZ comes with a bash completion script that would allow you to use tab completion for all of the parameter names and some parameter values. So if you have that, it makes remembering all these parameters a lot easier, because you can just use tab to help you out. But it's really not that complicated. You only need to remember a few keywords. So to create a container, you say vzctl create, and then you give it a container ID number. And I usually use the last two quads of the IP address, so I have a unique identifier for my container. And then you say --os template, and you refer to one of the os template tar gzip files that are in the /vz/template/cache directory. And then you have to give it a base configuration to use, and what that will do is when you create a container, it'll take a sample configuration file, copy it to the containerid.conf, and that'll be that container's configuration. Okay, so that will basically create the directory in the private VZ private. It'll extract the tar gzip file to that directory, and then it'll make a configuration file. And that's the basics of creating a container. It only takes, depending on the speed of your hard drive, it only takes however long it takes to extract that tar gzip file. And most of our OS templates are fairly small when you compare them to the full-blown installation media that you download on CD or DVD. Many of them are about 100 megs, between 50 and 100 megs. So however long it takes to extract that file is how long it takes to create a container. Of course, there are some additional parameters that you want to set after you've created it, like you may want to give it a name so you can refer to it by name rather than number. You want to give it an IP address, and this --IP add flag is what you do. To give it IP address, you give it a host name. You tell it what name server it's going to use to resolve host names, and that just adds, references in the etc resolve.conf inside of the container directory structure. And then you want to give it a disk size so that the quota package knows how big, the disk is. And then the --save parameter at the end will save that to that container's configuration file. If you leave off the --save, OpenVZ has about 20 different resource parameters, and all of them are dynamically changeable. So you can change the IP address, the host name, or how much disk space it has, or how many processes it can run dynamically. And that'll just change it in the container that's running immediately after you hit enter. But the --save will write it to the configuration file, so that parameter is saved to the configuration file, and so the next time you start the container, it'll know about that configuration change you made. Alright, mentioned we have about 20 different resource parameters. There they are listed under the set command. There's a whole lot of them, and I'm not going to cover them here, but you can see there's one for, you can limit how much CPU usage a container can have. It's disk space. What else here? Number of processes, a lot of them related to memory. What name server I already talked about. Whether it should start up on boot or not of the physical machine. All sorts of things. The parameters that are valid for create are --config, --hostname, --IP, --os template. And then if you wanted to change the location of the private and the root directory, those two parameters are with those. You can do it with those two parameters. Now, the OpenVZ CTL package comes with a number of programs, actually. You got the VZCalc, which allows you to calculate the container resource usage. There's a program to help you validate the container configuration file. So if you manually edit that and you want to make sure you got all the parameters right, you can validate it with this command. There's a CPU check command that shows the CPU utilization of your containers. The VZ list program is a little shell script, a little program that you run on command line that will list your containers and show you what their IP addresses and host names are. There's one where you can display memory information used by your containers. If you wanted to know what process on your host node belong to what container? The vzpid program is that. Now there are two programs here that I use a lot. I don't use most of those very often, but the vz Split and the vz Migrate I use a lot. vz Split, what it allows you to do is generate custom configuration samples that are geared towards your particular hardware. So how big is your disk? How much memory do you have? How big is the swap partition on your hard drive? You can say vz Split, and you can say split this hardware into X number of containers, and it will generate a sample configuration that will chop up the hardware evenly into exactly that many. So you could generate a sample configuration for 50 containers, and then you could look at how it set the parameters and get a better idea of how the resources are allocated. Now the Vz Migrate script allows you to do migrations of containers from one physical host to another, and that allows for offline migration where it shuts down the container on the source physical machine and then starts it back up on the destination machine. And we also offer, openvz also offers live migration, where you can migrate the container from one physical host to another without any downtime or loss of network connections. And it does it in a very transparent way where there's only a few seconds of noticeable network interruption. Offline migration, or non-live, also offers a pretty brief period of downtime. How long does it take to stop the processes in your container and then start them back up? Unless you have a really big container with, say, a big Java server or something, it usually only takes 10 or 20 seconds to start the container up. So the downtime of an offline migration, I would say, would be 30 seconds or less, generally speaking. Okay, now containers are coming to the mainline kernel. Andrew Morton, in some of his speeches about the future of the Linux kernel in the last year or so, he's been saying, well, the only thing I can guarantee a major new feature coming in the future is containers, because he's aware of a lot of different people working together on the containers. There's IBM, Google, Parallels, openvz, and the Linux vServer project, among others. And so there's a lot of efforts going into putting container features into the mainline kernel. And that all started with the 2.6.24 kernel. When I recorded this, the 2.6.27 kernel was the current mainline Linux kernel. And so with 2.4, 2.5, 2.6, and 2.7, a lot of container features have been added, and they'll continue to be added in the future. Now, these various features that you need to do containers are called various names: C groups, group scheduling, network namespaces, PID virtualization, memory controllers, etc. So all these different subsystems are being modified in the mainline kernel to be container aware and to provide container features. Since I'm gearing this presentation around openvz, I wanted to mention how the Parallels and openvz people have been contributing to the mainline kernel. And here's a little graph showing where they stand and how many patches they've done on each version of the kernel since 2.6.13 running up through 2.6.25. And you can see with 2.6.25 they had 278 patches that got accepted into the mainline kernel. And with the 2.6.25 kernel, that put them in the top 10 list for contributors to that particular version of the kernel. There they are, Parallels, 2.2%. And then so far as individual developers, the main developer for Parallels and openvz, he was in the top 10 list of changes that were accepted to the kernel at 1.3%. So as you can see, the openvz project is contributing a lot to containers going into the mainline kernel. Alright, now that we've gotten all that talky stuff out of the way, I can actually show you a demonstration. During this demonstration, I'm going to create a container. I'm going to show you what the container looks like from the host node perspective. Then we're going to go inside the container and see what the container looks like from within. Then we're going to examine the user bean counters file, which is an accounting of all the resource parameters that I've mentioned. And then we're going to discuss briefly container migration, and then we'll destroy the container. Okay, so let me switch over to my shell here. Here I am on a host node running an openvz kernel. Oops. There it is. It's 2.6.18.92, and it was compiled on November 14th of 2008. Now I can use a vz-list command with the -a to show all containers, even though those that aren't running, I don't have any containers. So let's create in vz-ctl. Let's see, there's all the flags that the create has. Actually not create, but so when it say just create, we want to create a container 199.055 because that's the last 2 quad to the IP address. And then I want to give it a host name of devel2.cs.montana.edu. Give it an IP address of 153.90.199.55. An OS template, I want to use CentOS 5. That's 5.2 based, and I built that OS template on October 10th. And then I need a config. I'm going to use the Split 32, which is a sample configuration that chops up my hardware into 32 equal containers. And then I hit enter, and that's going to extract the big tar.gzip file that represents CentOS 5.2. And we'll look at that here in a second when it's done extracting it. Now, like I said, depending on how big this OS template is and how long it takes to extract to the file system, it can take 30 seconds to a minute or so. There we go. So what did it extract? There it is. And that's about 160 megabyte OS template. That's a fairly large one. And let's look in the VZ private directory. I've created and destroyed a lot of different, migrated them. But there's the directory it created. So let's cd into that directory. And inside of there, you'll see the file system that you'd expect from a CentOS file, CentOS 5.2 Linux distribution. Let's go into the vzconf directory, and there is the configuration file that it created. It copied it from the Split 32 sample. So let's look at that real briefly here. On my machine, it says it can run, a 32nd of the maximum number of processes it could run would be 5,130. That's actually huge. So that's a lot of processes. So you can see here all the default resource parameters generated by that Split 32 configuration file. But down at the bottom, you'll see the unique parameters that we set when we created it. So we've got an IP address, a host name. It sets its root and private directory. It tells us what OS template it was created from and what sample configuration file it was created from. Alright, so when we run vz-list now, we can see that we have a container. It's not running, but some of the basic parameters are set. Let's set some additional parameters. vz-ctl set 199.055. Let's give it a name. Let's just call it devel2. Let's give it a name server configuration. Our name server here is 153.90.192.10, and I'm going to give it a disk space of 10 gigabytes. And I'm going to save that to configuration file. So let's look at the configuration file again and see down at the bottom all it did was write out the name server and give it a name. Somewhere here it will have modified the disk, but it's eluding me at the moment, but it's here. There we go, disk space. So that's 10 gigs basically. And you can also set the inode. That's another parameter, but I didn't set that, so it took it from the Split 32. Okay, so now we've created a container. We've set everything it needs to be on the network and communicate and look up host names, and it has a 10 gig disk space. So let's just start it up. And you'd use the start parameter, vz-ctl start, and we can either use the container ID number or we can use the name, and then just hit enter, and it'll start the container. And so it took about a minute or less actually to create the container, and then it took a few seconds to configure it and only a few more seconds to start it up. So the container's running. Let's run the vzlist command again. And you can see there are 17 processes. This is number of processes. There's 17 processes running in it now. And let's see how that looks from the host node view. I'm going to use the pstree command and give it a few flags there and then pipe it to less so that we can look at it. Now the init process is the very first process that starts up on a Linux machine, and it is the mother of all processes. So there's only one init process usually, but if you look, we'll search for the word init here, and we notice there's another init process, and it has quite a few children processes. And from the host node context, it's process ID 25095. And you can see all the child processes that are underneath it. So that init is really our container. And here are all the processes. Now you can see all of these processes that the host node has running. A lot of them are kernel threads. This big, all of this stuff are kernel threads that the Linux kernel needs to manage everything. Actually, those are under kthread, and all the rest of these are other kernel threads for various kernel functions. So we're saving a whole lot with the container, because the container really only runs the services that we want. There's not the overhead of an additional kernel. So we're running syslog, and you could trim this down to only the services that you want. If you don't want a syslog, you don't have to have it. We've got a syslog daemon, an SSH daemon, xinetd, which I probably don't really need because I don't have any dynamic run-on-demand services set up in this particular OS template. Sendmail, 2 processes associated with that, and then the Apache web server and all of its child servers, and then cron. So that is a pretty lightweight container. Now let's enter the container. Of course, we could SSH to it, or we could actually browse it. Since the Apache web server is running, I'll go to devel2.cs.montana.edu, and we get the default web page from CentOS. All right. So let's go back. Now we'll enter the command, enter the container with vzctl, enter, and then the name of the container, devel2. Now you can see the prompt change, so I know that I'm in devel2. And if I do a pstree inside of here, you can see here's all the process that we expected, and we've got some additional ones because we've entered into the container. We've run in pstree and less, and we've got a bash shell. So those were added just by entering it. But from within the container, it's init processes 1. So all of these PIDs are virtualized. From within the container context, these PIDs are different. Now, PID virtualization or process ID number. Process ID number virtualization is necessary because, like I said, openvz provides a feature called live migration and offline migration with the Vz Migrate script. So what would happen if you migrated process X from host A to host B? What if there was already a process X on host B? Well, you would have a process ID collision. You couldn't have 2 processes with the same process ID. So that's why it's important for openvz to have PID virtualization. Alright, so that's what it looks like to be inside of a container. You have all the normal programs, and you can create users and services. Something I wanted to show you is the user bean counters file. And what that is a special file in the proc file system that shows you an accounting of all of the process, all of the resource parameters. I'm going to reduce the font here a little bit so that'll look a little better. Wow, this font's getting small, and you won't probably be able to see it too well inside of the screencast, but there we go. So there we go. Here's container 199055, and these are this column represents the various parameters that you can have. KMEM size, locked pages, priv, VM pages, and you can find what all these various resource parameters are on the openvz website in the user's guide, and there's also several wiki pages. But some of them that are pretty easy to understand are number of processes. Right now we're running 20 processes. The most processes that have been run during this life cycle of the container is 25, and of course our limits are 5,138, which is quite large. Now the main thing you want to look at here is this fail count column. How many fail counts are there? And what a fail count is when you've set your resource limitations or resource values on a container, if you try to start up more processes than you've allowed the container, it'll fail. It'll fail to be able to create additional processes beyond the limit that you've given. Well, if you have a problem with a service in a container, you want to see if there's been any fail counts, and if so, then you want to increase that value for that resource so you can avoid that failure in the future. When you're wanting to put a container into production, it's pretty important to test it out for a while and get the resource value set to where you don't have any failures. And there are two main philosophies on how to adjust the parameters, and that is start with the really minimalistic values for everything, and then monitor your fail counts and then increase all the values that you need, or start high and stay there as long as you have the resources for it. But if you want to fit more containers on your physical host, then you can tweak those values down. So either start low and work up, or start high and work down. Once you learn how these resource parameters work, it's really easy to manage a container. Well, anyway, let's do a software update here, and you can see acts like a normal machine. I can have multiple containers doing yum updates or apt-get updates or what have you. I can install various software on there. Each container has its own IP address, so you don't have any port where you have port conflicts, because each one has its own network interface with its own IP address. Quite a few updates since I originally created this OS template back in October. But it acts just like a real machine. You can create accounts on it and do whatever you would to a normal machine. Now there are some limitations. You can't load modules within a container. You can't partition hard drives. You can't mess with the network interface parameters. So you can give someone a container and be rest assured that they're not going to mess with any other containers on the machine. The isolation is very strong, so they're locked out. They're locked within their container and they can't get out of it. They also can't mess with the host node container. But anyway, that's what OS virtualization is about. How long did it take to create a container? About 30-ish seconds. How long did it take to configure and set it up? Once you know what you're doing, just a few seconds. How long did it take to start? Not long. So that's about all I have to show. Oh, I want to show you the dynamic resource changes. Let me increase the font size now. Oops. Back to what it was. So right now our container thinks it has 10 gigs of disk space. Let me exit my container. VZCTL set devel to disk space. Let's change it to 20 gigs. Let me enter it again. Now do a df. Now it thinks its hard drive is 20 gigs. So you can see how dynamically changeable these resource parameters are. It's pretty nice. Alright, now I've mentioned migration. The vz migrate command is what you use. I'm going to go ahead and migrate this to another container, to another physical host. Vz migrate dash r no dash v for verbose keep dist. I'm going to do a live migration to another OpenVZ host named openvz1, and then the container ID that I want to migrate is 199.055. Now that's going to rsync the directory structure for the container from the host openvz2 to openvz1, and once that's synced, it's going to checkpoint the container. Then it's going to do a really quick second rsync to update any files that got changed during the process, and then it's going to transfer the checkpoint file over to the destination host. Then it's going to stop the container on the this host and start it up over there from the checkpoint, and there's not going to be any downtime. So if I do a VZ list now, oops, I'm openvz list. You can see it's not running here, but let me SSH to openvz1. You can see now I have quite a few containers running here, but there's our devel2 container. And if we enter it and get it's been up 10 minutes. So, I mean, it hasn't been running long, but we just migrated it and it didn't lose any downtime. So let's migrate it back. Vz migrate. I'm not going to explain these parameters. They're in the man page for it, but the online means do it without stopping the container and maintain the uptime. I want to migrate it back to openvz, and the container ID that I want to migrate is that one. Oops, I'm within the container. Vz migrate. It's going to migrate it back. It's going to be a lot faster because I kept the copy of the file system on the other node. That's what that -r no is about. Don't remove the file system. Okay. Do a VZ list. We can see the container's not there anymore. I'm going to exit that, and it's back on openvz2, and you can see the container's there now. And I look at the uptime, and it's still there. And our processes are still running. So live migration is really nice, as is offline migration too. Okay, so we did the demo. Now let's destroy that container. Well, before you destroy a container, you have to stop it. If you try to destroy it, it'll tell you need to stop it first. Stop devel2. You can see it stopped. And then that's going to destroy the container. It's going to move its config file to .destroyed in the etc.vz conf directory. It's going to totally remove the file system. Unfortunately, it doesn't ask you, are you sure? So you got to be really positive you want to destroy it when you enter the destroy command. At least if it's running, it won't let you destroy it. Okay, so we've done everything I wanted to cover in the demo. So let's talk about the future of OS virtualization really quickly. Once container features make it into the mainline kernel and our stock feature Linux kernel, they'll be available to everyone. There won't be this process of installing openvz. So what's going to happen once that becomes a normal feature of the kernel? Well, I think you'll start to see distributions provide OS templates for each release, so that, you know, in addition to their install media for installing on a physical machine, some of them will have OS templates so you can make containers out of. So getting OS templates is going to be a lot easier, I believe. And you might see special purpose application OS template. So not only is it a Linux distribution, but it's pre-installed with various services, or some application that doesn't even come with the distribution, pre-configured and set up ready to go. So you can create a container with LAMP or with Zimbra or what have you. You know, the possibilities are endless. You might be able to see clustering and shared storage solution features added, so that it's now in our live migration it uses rsync over SSH to transfer the file system back and forth. But if you have a container that has a really large file system, it might take a while. But realize there's no downtime associated with the transfer, because the initial transfer, that initial rsync, is done while the containers are running. So the vast majority of the file system is transferred while the container continues to run, and the container is only shut down when it makes that checkpoint, does the second rsync, and then brings the checkpoint back, restores from checkpoint. So the downtime is pretty small. But imagine once you have shared storage solutions, which are generally expensive, so it's nice that openvz doesn't require shared storage, but I can see in the future, when containers are part of the mainline, that containers become aware of shared storage, so that you've got a SAN or a NAS shared between two or more physical hosts. Instead of having to transfer the file system, it can just unmount the disk partition on physical host A and remount it on physical host B, and then start up from checkpoints. So that would change how long it takes to do the migration. And probably the downtime would be reduced as well, I'd imagine. I already mentioned the appliance server product concept about having various applications pre-installed in the OS templates. This could lead to new security application models. Now that you can put things into a container, maybe services that server applications that are provided by a distro could be packaged in such a way as you can put them into a container easily. Just I want a DNS service container. Boom! I don't have to have the entire distribution, just enough to support that. That would be awesome. And then, of course, we'd love to see more advanced GUI management applications for containers. Well, I kind of rambled on for a while, but hopefully you have a good understanding what openvz is and what it can do and what containers are good for. Now, I don't try to claim that they'll do you'll be able to virtualize and do everything you want to with OS virtualization. There are some limits, but it's nice to have fully virtualized hardware machine virtualization products as well as OS virtualization. I think it'll do both of them. It covers a wider range of virtualization needs. So I'm glad we have both. And the Linux kernel already has the KVM for fully virtualized machines. And so once containers will be in there, you'll have both. So there's the openvz web page. And there's the Linux vServer web page, and there's parallels.com where you can learn about Parallels, Virtuoso containers, and there's my website and my email address. Thanks for watching.